Hello and welcome to week 3, lecture 2. Today we're going to be talking about projectile motion. Projectile motion is motion near the Earth's surface where the projectile is launched at some angle, and then in projectile motion, the object travels in a parabola. So we have our diagram here of a baseball that's launched at this angle phi naught. That's the symbol phi, if you weren't familiar. And then we also have a free body diagram showing that the only force acting is the weight of the ball. The initial velocity is at an angle, as we saw. So we have to break it into components. The initial x velocity is v naught cosine of phi naught, and the initial y velocity is v naught sine of phi naught. And again, the only force acting is the weight force, so we can get our sum of forces equations. And we see that there is no force acting in the x direction, so it's just 0. And in the y direction, it's negative mg. And from this, we can get the components of acceleration also. So x acceleration, unsurprisingly, since there's no force in the x direction, is 0. And y acceleration is negative g. And so just acceleration due to gravity pointing straight down. Based on the acceleration and initial velocities, we can adjust our equations our kinematics equations for this situation. So from this velocity equation, for x, we just get that the velocity is constant. And for y, we get the velocity is given by v naught y minus gt, our time. And for the long kinematics equation, we get that the position in x is just the initial x velocity times the time. And in y, it's the initial y velocity times the time minus 1/2 g times the time squared. The horizontal range is given by this equation, which can be derived by the equations on the previous slide, but I didn't want to do it. It's in your textbook if you really want to know the derivation. But the range is the horizontal distance where the projectile returns to the height it was launched at. So if it was launched from the ground, then the range is the x position when it hits the ground again. Or if, in this example, it was launched from a certain height, the range is the x position when it reaches that same height again. And just for your knowledge, the maximum range, so the longest x distance that you can get a projectile to go, has a launch angle of 45 degrees. And here's snapshots of an object being dropped, one object being dropped, so this one, and then the other object starting with some initial velocity. And you can see that it moves in a parabola. And the thing to remember that for projectile motion, the acceleration is just the acceleration due to gravity, and it's pointing in the negative y direction the whole time. And another thing, actually, in looking at this diagram, you can see that along the trajectory, the velocity is tangential to the parabola, that is the trajectory. And you also see here that the y velocity is 0 at the peak of the motion. And actually, I think, yeah, we're going to use that in this example problem that we're about to do. So let's work on this example. A soccer player kicks a ball at an angle of 36 degrees from the horizontal with an initial speed of 15.5 meters per second. Assuming that the ball moves in a vertical plane, that just really means just like not in an additional depth. That's all that means. Find the time at which the ball reaches the highest point of its trajectory, its maximum height, its time of flight and range, and its velocity when it strikes the ground. So lots of things. Okay, so we should start out, as always, with our knowns and unknowns. So the initial velocity is 15.5 meters per second at an angle that we'll call theta of 36 degrees. And the initial y position is 0 meters. And we'll also just define the initial position as our origin. So we can also say that the x position initially is 0. And this is projectile motion. So the y acceleration is -g and the x acceleration is 0. And then there's lots of stuff we don't know, especially because there's lots of stuff we're asked for in this problem. So we don't know this maximum height. We don't know the time to the maximum height. We don't know the range. We don't know the total time. And we don't know the final velocity. Okay, one thing I want to do is just kind of draw the situation a little bit so that we can break it up into parts. So I'm going to just draw our trajectory. So one of the things we want is at this point here, the y max, maximum height. And at this point, we'll call this T1. It'll just be time 1. And the velocity in y at that point is 0. Remember the peak of the parabola, the y velocity is 0. The x velocity is not 0 at that point. And then the other point we care about is T2, which is kind of T final, or the total, which I wrote there. And at that position, the y position is 0, and we don't know what the velocity is there, but we'll need to find it. Okay, cool. Now let's take a look at our velocity and break it up into the components. So this is v naught. Doesn't really need the vector, but that's okay. V naught x is v naught cosine of theta, and that's just because this is the x and it is adjacent to the angle. And then v naught y is v naught sine of theta. That's because it's opposite the angle. Okay, so now the first thing we want to find is T1. And at this point, we just said that it's the maximum height, and it is when the velocity is 0 at that point. We don't know what the maximum height is, so that doesn't really help us right now. But the velocity being 0 does help us because we can use this equation. V1y equals V naught y plus AY T1. And this is 0. So if we can solve for the time by subtracting v naught y from both sides, give us negative v naught y, and then dividing the acceleration on both sides. That gives us time 1. And so this is negative, let's see, v naught sine of theta over negative g. So those negatives cancel out, which is good because we don't have negative time. So let's plug in our numbers. 15.5 meters per second times sine of 36 degrees. Let me check it. Divided by 9.8 meters per second squared. That gives us a time to peak height of 0.93 seconds. Okay, well, if we know that time, then we can find the maximum height, which is good because that's what they asked for next. So the maximum height, which we're also calling y2. And now we have the time to that, time 2, of 0.93 seconds. And we know, again, still that we're going to use the long kinematics equation, so our initial velocity doesn't actually matter. Or, sorry, our velocity at this point doesn't matter. Our initial velocity doesn't matter. And I'll say y naught is 0. So we're going to use this. y2 equals y naught plus v naught yt plus 1/2 ay squared. Okay, so just that goes away, and this is what we're solving for, so we don't have to rearrange anything, so that's nice. y2 equals v naught sine theta times time plus, minus, because it's negative g, minus 1/2 gt squared. You plug in our numbers, 15.5 meters per second times sine of 36 degrees times 0.93 seconds minus 1/2 9.8 meters per second squared times 0.93 seconds squared. And this gives us, I'm sorry, I just realized I've been calling this y2 for this part of the solution, but it's actually, we were calling this y1. y2 was 0 at the very end. So let me correct that really fast. There we go. Okay, so that gives us y1 equals 4.2 meters. So that's the maximum height. Next up, they asked for the total time. And I'm going to, I'm actually just gonna add a page because we ran out of room. So we want the total time, or this one is actually what we're calling T2. And for this, let's see, y2 is 0. And I think that maybe is all we know. But I'm going to tell you something. The time, the total time is actually equal to 2 times the time to the maximum height. So that's just a helpful hint. We're still going to solve it because we might as well. It's good practice. But if you're short on time, it's funny because that's the time. Anyway, y2 equals y naught plus v naught y t plus 1/2 ay t squared. Both of these are 0, and we're trying to find this time. So we have 0 equals v naught yt, and I'm going to plug in for g here, minus gt squared. But this equals 0, and both terms have a t in it, so we can just divide everything by that and get rid of one of those, which is nice. Okay, and now we want to solve for t, so we'll subtract that velocity on both sides, so negative v naught y, and then we will divide both sides by 1/2 g. And dividing by a fraction is multiplying by the inverse of it, so the 2 goes on top of our fraction here, and we have g here. Sorry, just lost track of the negative sign. I needed to divide by negative 1/2 g. So both of these negative signs go away. There's this, there we go. So the time is 2 times 15.5 meters per second times sine of 36 degrees divided by 9.8 meters per second squared. And this gives us a total time of 1.86 seconds, or 1.9 seconds. Okay, now the range. And in our case, this is the position in X at this kind of total time, because in this example, the ball was launched from the ground. And this is just X position 2. And the time is T total, which is 1.89 seconds. I'm sorry, 86 was the number. I feel like I said 89, but it's 86. 86. 1.9. You could round it to. Okay. So we can just use the long kinematics equation for this. X2 equals X naught plus B naught X times time plus 1/2 AX times squared. This is 0 and that is 0. So just like I showed in the slide, the X position is just the velocity times the time. Is 15.5 meters per second times cosine of 36 degrees times 1.86 seconds. This is 23.3 meters. That's what x2 is. Okay, now the final velocity. The final. And I'm going to give that a vector hat because we're finding it in both directions. Okay, so at this point, we have the time of 1.86 seconds. Our y position is 0. Our x position we just found is 23.3. What else do we know? Acceleration is y, still negative g. Acceleration in x is still 0. And we know x and y based on the initial x velocity. Sorry, skipping words. Okay, so let's find actually, let's use this equation. V final equals V initial plus AT. And for X, and we know this already, but I'm gonna just show us again. V naught X plus AT, but oh, that's 0. So this is just still V naught cosine of 36 degrees, which is 12.5 meters per second. And then in the y direction, we have the y equals v naught y plus AYT. And this one, none of those are zeros. So we have to plug stuff in. 15.5 meters per second sine of 36 degrees minus 9.8 meters per second squared times 1.86 seconds. And this is negative 9.1 meters per second. So it looks like we still need a little bit more room. So now we have our velocity in x, which is 12.5. It didn't change in this situation. And velocity in y, which is negative 9.1 meters per second. And our total velocity is just the square root of those added together. Equals the square root of 12.5 meters per second squared plus negative 9.1 meters per second squared. And that is 15.5 meters per second. And finally, we want to know what the angle is. And I said this in the example problem from the last lecture. Will that be? We have to define where we're taking the angle from. So for this, we're just going to take it from here. I'm going to call it phi because our launch angle was theta. Hopefully I don't sneeze. Sorry, feel sneeze coming on. And so phi is tangent inverse of y is still gonna be opposite and x is still gonna be adjacent. So vy over vx equals tan inverse of, and because we're going to be careful about our labeling, like you could write this, we can put in negative 9.1, that's fine, but you don't have to as long as we are careful in explaining what this angle is from. But if we plug in negative 9.1, we get negative 36 degrees. But V final is 15.5 meters per second at 36 degrees clockwise from the positive x direction. Okay, so I'm going to just briefly go back through this because this was a long example. So we have someone kicking a soccer ball from the ground. We at an initial velocity of 15.5 meters per second and then a launch angle of 36 degrees. And we had a bunch of stuff to find. I drew out our trajectory so that we could kind of break up where we were looking for things. So the first thing we wanted was the time to the maximum height of the trajectory and the maximum height itself. So that's what this was here. And then the other thing we wanted had to do with the total range or the total time of the projectile's motion. So to find the time to maximum height, we had to remember that at the maximum height in the trajectory, the y velocity is 0. So that's what we did here. We set that y velocity equal to 0 and solved for time and got 0.93 seconds. And then now that we had the time, we then were able to use the long kinematics equation and solve for the maximum height at that time, which is 4.2 meters. And then we were able to find the total time, which I told you is actually just 2 times the time at the maximum height. But we also solved for it too, and we got 1.86 seconds. And then we found the range, which is the x position at the maximum time, or like the time of the entire trajectory in this case, because it was launched from the ground. But do remember that the range is when the x position when the object is at the same initial y height. Anyway, so ours was 23.3 meters. And then we found the final velocity. We needed to find it in x and y. So in x, we found, well, we knew that it didn't change. There was no acceleration. So it was 12.5 meters per second. And then in y, it was negative 9.1 meters per second. And then we needed to find what the total velocity was, which ends up being the same as in the beginning, 15.5 meters per second. Direction's different though. Instead of being launched up at 36 degrees, it's down at 36 degrees. Okay, that is everything. I hope you have a great day.